Let us look at this problem right here. We have a box, well, not a box, but one object that is designed to be placed on this surface. We have the angle, and we have the static coefficient of friction, 0.2, and the kinematic coefficient of friction, which is 0.5. We have they're already given us the force of this object um, on the vertical direction. It's 800 newtons. And they're telling us that there's a mechanism that allows this lever to move at a certain angle in a force P. And then obviously at certain angle and certain force P, you can move the object up. So there are two variables here. We have P and we have theta. So that the force at a certain theta is has to be large enough to overcome the friction force at this angle. So the question is determine whether the block shown is equilibrium and find the magnitude of the friction force when theta is equal to 40. So they're giving us this info right here. And P equals to 400. So they're giving us that info as well. So theta is 40 degrees and P equals 400 newtons. All right, so the first thing we need to do is choose our coordinate system. If we choose a coordinate system that is like so, horizontal x and y, the force of 800 newtons like so, this is 800 newtons, then we're going to have P at angle theta, and we're going to have friction force, which is not necessarily, it's not going to be 40 degrees, it's going to be something else. Friction force, and this is 25. Also, we're going to have a component of perpendicular force because of the ground. So the normal, actually I like calling normal little n, lowercase n, so it's not confused with newtons. So then you have to find this angle right here. That's approach 1. Approach number 2 is to choose the coordinate system parallel to the ground. Where we have a normal force right there, and a force of friction, which we don't know which direction it is, but if they're pulling this up, it could be going the opposite direction, or actually we don't know if they have to pull it so that it doesn't roll or doesn't move back, so we can say that direction right there. That's our friction force. Then we have 800 newtons vertically like so, and we have a P. And I think this is easier because they're really giving us the angle right here. You know, this angle right here. So let us try approach 2. Okay, so let's go ahead and draw the system that we're trying to pull. And we said that we're going to have a coordinate system where our normal force is right here. And our 800 newtons are acting vertically. And we have a force of friction right there. And then we have a force P going like that. So if you notice, we should have information about the angles as well. So let's try and find out what we know. The first one is pretty easy. This one is 25 degrees, which is right here. Let's fix this a little. 25. And we have force P I'm exaggerating force P. And that is 40 degrees. So 40 minus 25, we have that this guy right here is 15. Because 40 minus 25 is 15. Okay, so we have 15 and 25. So that means that this force with respect to y, if we choose x and y, we know that this angle with respect to y is 15 degrees. And if you notice, this and this, x and y obviously are perpendicular, therefore we have 90 degrees. So we should be able to see what is our angle right here. This is 25. So this x-axis is 25 from the horizontal plane, and this 800 Newton force is perpendicular to friction. So if there's 25 newtons between this x prime, which is the horizontal plane, and this f, so if we move this 90 degrees, we're going to have a horizontal, and basically this is also 25. So this is 25 degrees. Why? Because this plane with respect to this horizontal is 25. So if we rotate 90 degrees, this will be horizontal y, and this will be the axis right here. Right, you see it? Let's see if we can see it here. This is the surface, it's 25. But that surface is where we have the force of friction. Then we have a perpendicular force, which is our 800. The 800, sorry, the y-axis. The perpendicular line is the y-axis. And we have a vertical force, which is 800. This configuration is the same as this configuration, because this one is 90 degrees with respect to that one, and this one is perpendicular to that one. So as you see in friction problems, the most difficult part is setting up the geometry. Okay, so we have 25 degrees. So let's do summation of forces in Y. Let's see if we need any more information. And remember, this is going to be the system that we're going to follow. Y, X. Okay, so summation of forces in Y, we have a positive normal force minus, this is going to be this component, 800 cosine of 25, and we have one more component, which is force P, and in Y will be this component right here. So this is going to be plus 400 times sine of 15, because our, um, our axes are this one and that one. So we have 15 degrees between P and that axis. Okay, this is equal to 0. So we have one equation, one unknown. We should be able to compute this guy. And equals to 800 times cosine of 25 minus 400 sine of 15. Then we know that our normal force is equal to, let's see, 800 times cosine of 25 minus 400 times sine of 15. This is 621.5. 621.5. And this is positive, therefore this force is going up. Okay, so we found force, the normal force. Remember and try and write this normal force as a lowercase. The normal force, it should be a lowercase, so we don't confuse with newtons. Okay, then we can do summation of forces in X and find P. Well, actually, we already have P, but with summation of forces in X, we can find the friction force right here. So summation of forces in X equals to 0. Remember that our positive X is going to be this configuration right here. So the system of equations will be friction, which we set it up negative friction, then positive. This is 800 and sine of 25, 800 times sine of 25 degrees, right? Because we have this component like that. All right. And we have negative 400 cosine, because it's going in that direction. Cosine of the angle, which was 15, equals to 0. This is the angle right here. This angle is 15. All right. So we can solve for F, which is equal to 800, well, let's do that. 800 sine 25 minus 400 cosine 15 is negative 48.2. Negative 48 newtons. Okay, so the force of friction is negative 48 newtons, which that means that actually is going this way. Therefore, The system of equations is telling us that this is indeed moving and the friction is what's preventing it from going faster or whatever. If the force was going the opposite direction, it means that this is not moving and the force, the P, is not large enough. But basically what this means right now is that P is greater than the force of friction. So the system is moving. All right. So let's see if they have any other questions here. So determine whether they're in equilibrium and find the magnitude and direction of the friction force. Yeah, so the friction force is negative 48, but we can do, they're giving us the kinetic coefficient of friction. So if the force to see if it's moving is going to be the static coefficient times the normal force. So static coefficient was 0.2 times the normal force, which was 621.5. So this is 20% of this. So 621.5 times 0.2. 621.5 times 0.2. That is 124.3. So that is the friction force. And since the force that we found in the system of equations right here since this force is less than the force of moving, then the force that they're applying to move, this is the force needed. This is the force needed for the block to move. And right now, we're seeing that with this P, the force right here is only 48. So the way you understand this is that the force is not, the block is not moving. Because in order for the block to move, the friction force has to be, oh, actually, hold on, this is moving. It is moving. Because the friction force is, nope, I apologize. Because the friction force is greater than the actual force that the system is seeing at that with the P applied, so not moving. In order for the block to move, the force here will have to be greater than the friction force. Okay, so that's how you read this problem.